Alright, look at this monster. Yesterday I said that I was going to show you a windmill that would meet situation B of the windmill challenge. Situation B is where input speed is greater than output speed. In a situation like that, you're going to have more torque. So it's going to have more power to do heavy work than what is being put into it. So if we were looking at a wind situation where it was a light wind, just enough to move the blade, it would have much more force at the other end to do any sort of machining or grinding operation that the mechanism is intended to be used for. So I'm going to talk a little bit about this for a few minutes so that you can see how I was able to reduce power down. And I was a little redundant in it because I wanted it to be a fairly extreme change that is noticeable. And what I want you to look at is notice one revolution of the fan blade for the input gear versus one revolution of this large sprocket down here. This large sprocket is indeed our output. And even when you look at the other sprockets are moving much more quickly than the one that is on the end of the mechanism. And so this is achieved through a series of sprockets. Now, yesterday when I set up this gear train, I wanted to do a windmill that met situation A, where input and output was constant. And I was trying a different mechanism because I had used chain and sprocket and I had used bevel gear, so I wanted a mechanism that was using a simple gear train. And basically what I did was I built off of the simple gear train using more of the VEX pieces. But I had to find a way to change my gear ratios. Now, since I had such a large input gear up here on the tower already, I could have changed this situation by just simply putting a smaller spur gear on. But then the problem is I would have to realign all my bearings that I placed in the middle, and that was going to take some time. So what I did was I set up a second tower, and it's just a very thin tower right here, you can see, to set up my chain and sprockets, and they cross between the two towers. Now, since I just have a single fitting here, I fixed bearings on both sides because I told you before that these square drive shafts need to be supported in more than one position or they're just not going to be very stable. Remember, the requirement of the windmill challenge is to have a mechanism that is stable and rigid. And so I placed bearings excuse me, on both sides to give a more stable support of those drive shafts. Now, with the bearings close together, I was able to stay with a short drive shaft at the bottom, but I did have to find a slightly longer one at the top. Now, yesterday I told you I was saving space by placing my bearings inside the girder. This is our standard girder that we're working with. So just kind of remember that you're doing that as well. So then basically, to get my torque values up and my speed down, I went from a small driven gear off of my windmill output to a larger drive gear. And that already reduced it down. But I took it one step further by taking the output of that drive gear and putting another small drive gear behind it to our final drive gear down here at the bottom that is much larger. And the result is noticeable. It takes several revolutions of the fan blade to equal one revolution of the output gear. Let's analyze this. Let's see what our final ratio is. So if I place a mark here, we got that little blue mark. We want to see how many rotations it takes for that little blue mark to come back to the top. Here's 1, 2, 3, 4, 5, 6 and a half. 6.5 revolutions. So our gear ratio is 6.5 to 1. Our input must spin 6.5 times to equal 1 revolution. And this is something you're probably going to need to report on that sheet that goes along with the windmill challenge. Now, once you get through scenario B of the windmill challenge, have me check your work, and depending upon where we are at on time, I may have you start an advanced project. So until next time, good luck.